Yeah.
Okay.
Yes.
So I cannot see in this if I share the presentation, I cannot see the chat. So if someone has questions, I don't know.
Yeah. We will stop you this one, and then you can basically these participants they can ask.
Okay, so if they ask, please tell me because I cannot see the chat in the share screen mode.
No, actually, from our side, volunteer Nipun and Amit, actually they will inform you whenever some question will come.
Okay, thank you. How many people are expected?
In morning, we had around 45.
Okay.
Yeah, now they are joining because in India now is the 6:30.
Okay. Still not too late. Still not too late.
Yes.
They will be home by the dinner.
Yes. No, generally we have dinner around 8 o'clock, little bit late.
Okay, a little bit late.
Yes. Because Jodhpur is not that much cold.
Mm-hmm.
Yeah. So I think we can start this one.
We can start.
Yes. So yeah, good evening, all the participants. And today we have this one, Dr. Mathia. He is the electron microscopy expert, and we have the collaboration with this one. Dr. Mathia started, I think, in 2015, and we have done few papers together. And he is going to explain about how this SEM electron microscopy is basically working, how to capture the good image, how to do the data analysis, mainly for the functional material and other nano materials. So you can say he is one of the expert this one. So wherever you have the doubt, you can ask him this one. Yeah, so with this one, I invite this one, Dr. Mathia Fenetti, to please continue this tutorial.
Okay, thank you very much. Yes, if you have questions, please stop me anytime and feel free to ask. So today I will briefly introduce you to scanning the electron microscopy. First of all, let me tell you briefly who I am. I work at the University of Nova Gorica, and I'm professor at the School of Science. I teach some courses there, experimental methods, electron microscopy to the master students and also to the PhD students. I do a course of training of scanning electron microscopy. It is a course for PhD, and part of the slides that I show you today are from that course. Of course, you cannot come here to try, but I will try to give you a feeling of what is electron microscopy in hands-on experience. And I'm a researcher at Materials Research Laboratory. The head is Professor Ballant. And I'm also in charge to coordinate the electron microscopy facilities. In particular, we have here at university a scanning electron microscope, which is the one that you see behind me. And now, in this moment, I'm in the scanning electron microscopy lab. Then we have also a transmission electron microscope and a sample preparation facility room. But today I will only speak to you about the scanning electron microscopy. So briefly, I will introduce what is scanning electron microscopy, what are the basic principles, how the instrument is made, and some different kind of analysis that we can perform with this instrument. And in the meantime, I will also try to show you some hand-on experience, let's say. Okay. Okay, so let's start. A very important concept before starting with scanning electron microscopy. I would like you to highlight the concept of a map. What is a map? This is at the base of all microscopy techniques, not only scanning electron microscopy, but it is a very important concept. A map is a data set where a physical quantity, which can be, we have many examples of different physical quantities, okay? But in a map, a given physical quantity is measured with spatial resolution, and it is matched, the value of the measurement of the physical quantity is matched with the position. So a map is a data set where I have an area, okay, and the area is divided into a grid of points, and each point is defined by x and y coordinate, and in each point I assign the value of the physical quantity that I'm measuring. For example, the one that you are looking now is AFM map, atomic force microscope. And so the physical quantity that I'm mapping, that I'm plotting here is the surface height. So, and it is measured in nanometer because this is a technique which is very resolved in the height measurement. Okay, and so the data set, the map, can be represented as a matrix of x and y points. And in each point, I plot the value of the physical quantity that I'm measuring for, in this case, the surface height. So how to build a map? How to collect a data set of microscopy? Okay. There are mainly two ways to build a map. Two different approaches, let's say. The first approach is so-called spatially resolved probe approach. In this first approach, the measurement of the physical quantity that I want to plot, to map, is done in series in many precise points of the surface. So one point after the other. And then, after I collect all the points, I can assemble the map. Okay. And so in this case, of course, what is important is that I need a very sharp probe to measure locally the physical quantity. There are several different microscopy techniques which rely on this approach. And for example, I mentioned scanning tunneling microscopy, atomic force microscopy, scanning electron microscopy, which is the one that we are going to see today, and also other, of course. The second approach is completely different. In this case, I send toward my sample many probes, let's say, okay, in parallel. So I don't have a local measurement because I have a sharp probe. So I send all the probes in parallel. They interact with the sample, and then they are the signal, the effect of the interaction is transported toward a spatially resolved sensor. In this case, so the matching between the physical quantity and the position is done in the sensor, not because I have a sharp probe. And in this case, of course, there are many different examples, such as, for example, our eyes are working in this way, photography, classical photography, optical microscopy, transmission electron microscope, and other techniques that, of course, there are many. So these two approaches are in these two approaches, you can collect almost all the microscopy techniques. SEM, scanning electron microscopy, belongs to the first approach. So we need a spatially resolved probe, a sharp probe. So what is the basic principle of scanning electron microscope? In this case, in the scanning electron microscope, the probe is a focused electron beam. The beam of electrons is very focused, and at the incident point with the sample, it has a lateral size of few nanometer, let's say 1, 2, 3 nanometer, depending on the microscope. Okay, in the modern, let's say in the high-end microscopy, they can go also below 1 nanometer. Okay. So I have this very sharp probe, this electron beam, and when the electron beam is incident on the sample, it makes some interactions, okay, and several different products are emitted by the sample. Both either electrons, secondary electrons, backscattered electrons, also Auger electrons, and also some photons, some electromagnetic radiation. And typically, we divide them into visible light photons, so cathodoluminescence, and X-rays, okay, depending on the energy. So how does it work, SEM? I have this probe, which is incident on the sample, and I scan the probe over the interest area, point by point, and in each point, I collect one of these signals that I told you, for example, secondary electrons. And I measure the intensity of the emission in each point. Here you can see a brief video. So the probe is moved over the sample, and in each point I measure through a detector a signal, and I put it in the correspondent point in the image. Okay. So the map is produced by plotting the signal intensity at any probe point. And so, for example, this is an image of secondary electrons, and in each point, I measured the intensity of the secondary electrons, in this case, and I plotted in a grayscale the intensity according to a given scaling that I decided. Okay. Of course, well, what is the time scale of this kind of measurement? It's quite fast. So, of course, I can decide how long to stay in each point. Typically, we are in the range of microseconds. And so one image in a fast scanning mode, one image is acquired in less than 1 second or 1 second or 2 seconds, something like this. While a high resolution image, if I go slowly, and in each point I stay more, then it can take also 30 seconds or 1 minute, but not more than this. Okay. And this technique, it works, of course. And for example, this is a secondary electron image produced by SEM, the SEM which is behind here. So in each point, I measure the secondary intensity and I plot it on the image. Okay, and this is the result. Now, before going, I would like to give some details about the interaction between the beam and the sample to understand what are the different signals that we can analyze. No, but before this, I would like to do a short parenthesis about resolution, because this is a very important point in scanning electron microscopy. So the first thing to ask is why we use electrons, why it makes sense to use electrons. And well, the first reason is that electrons are easy to, a beam of electrons is easy to move and to locate, to precisely position it. Why? Because electrons are charged particles, and in order to move and to make exact position of the beam, I just need to apply some electric field, right? I can easily scan the electron beam by applying the electrical fields. The second very important reason for which electrons are very useful is because of resolution, of the achievable resolution. And to explain this concept, I show you these two pictures, and I ask you, what is the difference between these two pictures? The difference in these two pictures is exactly the resolution. And what is the resolution? The resolution is defined as the capability to distinguish between two different features in an image. Okay? So, for example, in this picture, in this bottom picture, which is at lower resolution, we cannot distinguish very well the different hairs of the squirtle, while here we can distinguish them better. Okay, so for example, these, I can see that these are different. Here, I cannot see that they are. So the resolution is lower. How can we define resolution in a physical way? The physical quantity spatial resolution can be defined as the minimum distance at which the two features can stay and still be distinguished. Okay, so this is the definition of spatial resolution. And what are the things which affect the resolution? The first very important thing is the interaction between the probe and the sample. If the interaction is very local, then I can acquire a signal which really depends on a short scale. While if the interaction is at a large range, of course, the resolution will be lower, right? And for example, we will see that, for example, in EDX, in the X-ray detection, in a scanning electron microscope, the resolution is much lower because the interaction volume, the interaction range is much larger. Then another important factor is, of course, the scanning condition, the scan rate, the integration time, the signal to noise ratio. Okay, if I go very fast, the signal to noise ratio is lower, and it's more difficult to distinguish between different features. Of course, the scanning sampling, so how many lines and point per lines I decided to collect. And also, very important, the environment condition. So if I have noise, if I have vibration or electromagnetic noise, I is more difficult to precisely locate the beam, and so the resolution is lower. And of course, also the display device can be a limiting factor for the resolution. I didn't mention here the most important factor which can affect the spatial resolution. And this factor is the probe size and the probe shape. Okay. So if I want to have a high resolution, I need a sharp probe. If I have a large probe, of course, larger than the features that I want to distinguish, then I have a lower resolution. To explain this concept, here I put an image which comes from another microscopy technique, actually, as scanning probe technique, but the concept is exactly the same. So if I have a feature on my surface, if I have a large probe, then the image is always true. The image will be the convolution between the shape of the feature and the shape of the probe. So if I have a large probe, I will have a larger image, let's say, of that feature. While if I have a sharp probe, I have an image which is more similar to the original shape of the feature. Okay. So why this is important? Because in the case of electron microscopy is the same, no? So in the case of scanning electron microscopy is the same. If I have a sharp probe, I have high resolution. If I have a large probe, I don't have. As I said, in the modern SCMs, the typical size of the probe is, let's say, about 1 nanometer. And so my resolution is also on that order of magnitude. And so the question was why we use electrons. So it happens that there is a relation between the best achievable spatial resolution and the probe wavelength. This is true both for optical microscopy and also for electron microscopy. From quantum mechanics, we know that also electrons have a wavelength, and so they can be described as somehow waves, okay? And there is a relationship between the D is the resolving power, the spatial resolution, and lambda. Here, what I want to highlight in this formula is lambda. Lambda is the wavelength of the probe. In this case, the wavelength of electrons. So electrons have a wavelength which depends on their kinetic energy. In a typical SEM, the kinetic energy of electrons is in the order of, let's say, from 1 kilovolt to 30 kilovolt. This is the typical range, okay? And so the correspondent wavelength, if we use the classical, but also if we use the relativistic relationship, they don't change much, okay, at this low energy. So you can see here in this column is given the wavelength of the electrons, for example, at 5 kilovolt or at 10 kilovolt. And you see that this is much less than 1 nanometer. If we use this wavelength to calculate what is the resolving power which is accessible through this formula, we see that, for example, at 5 kilovolt, the maximum theoretical resolving power is half a nanometer. And at 10 kilovolt is 0.4 nanometer. Of course, this is only the theoretical resolving power. The real resolving power is a bit worse, of course, because we have some aberration, we have some noise. Of course, we always have noise. The beam can be non-monochromatic. The emitter is not a single point. So there are several factors which influence the resolving power, and actually the real resolving power, for example, in our microscope is, let's say, at 30 kilovolt, which is the highest possible energy in our microscope. The resolution is 1.2 nanometer, and at 15 kilovolt, which is the typical energy that we use, is about 3 nanometer. Anyway, you can see that by using electrons, the wavelength is very small, and so the resolving power is very, let's say, below 1 nanometer, or anyway, around 1 nanometer. This is not the case, for example, in optical microscope, where if I use visible light in the range of some hundred of nanometer, I cannot expect, even theoretically, a resolving power less than, let's say, 150, 200 nanometer. Okay, so this was the parenthesis about the resolution. So now we know why we are using electrons. Let's go on. So what are the basic elements in a SCM? In ICM, the basic elements are the gun, which emit the electrons. This is typically at the top of the column. Then there is a column where electromagnetic lenses and other elements which are used to focus and shape the beam and also to move the beam, to raster the beam, are situated. Then we have the detectors of different signals, secondary, backscattered, EDX, and so on. And of course, we need a vacuum system, because I didn't tell you, but all these system, all this apparatus is under vacuum. So now I show you in our microscope. The gun is here, okay, at the top of the column. Then we have the column with several apertures which are used to filter the beam and shape it. Here there are also lenses and the scanning coils. This is the specimen chamber where I will put my sample. And then I have detectors. I can show you some. So this is the secondary electron detector from the outside. Of course, the important part is inside. I will show you later. This is the EDX detector. This is the cathodoluminescence detector for visible light. Well, in this microscope, we have an additional detector in lens, which is in the column, this one, for electrons. And then we have a backscattered electron detector, which is this, and I will show you later inside the chamber. So depending on the microscope, of course, you can have different detectors, and these enable you to do different kind of analysis. Just a few words about the gun. The gun, as I said, is placed on top of the column. There are three main kind of gun, of emitter: the tungsten gun, the lanthanum hexaboride emitters, and the field emission emitters. In this case, in our microscope, we have a field emitter, a field emission emitter. And here you can see an image of a field emission filament. It is made of tungsten, typically, and it has a very sharp tip. The sharp tip is required because the field, the electrical field, when you know that it depends on the local curvature, okay? And so if you have a very sharp tip, in that point, the electric field at the surface is very intense. And so for that reason, it's very easy, let's say, to extract by field emission the electrons. In order to make it even easier, typically the filament is heated at quite a high temperature, typically this, okay, in this case 1700 Kelvin. And by heating up and applying a very intense field, we can extract electrons out of the emitters, okay, which is inside here, and we can generate a current of electrons, which are the electrons of our beam, okay? The typical emission current in a standard SEM is in the order of 50 microamperes. So this is the number of electrons per second which are coming out of our field. Then we have we have some anodes here below the filament, and by applying a positive field to the anodes, we can extract, as I said, the electrons from the field. The so generated electron beam is then driven through the column, okay? And in the column, we have different electromagnetic lenses. Electromagnetic lenses are quite simple objects, actually. Are nothing else than coils of copper wire, okay, with a hole in the middle. And the hole in the middle is where the electron beam is passing through. How does it work, an electromagnetic lens? Briefly, I can tell you that by driving a current in the coil, we generate a non-uniform magnetic field in the middle, okay? And this non-uniform magnetic field has the capability to focus the electron trajectories. So it happens that since this is not, this is a scheme, okay? Actually, in this scheme, you see very large angles, but in the reality, the angles of the electron beam are very small, okay? If you could see inside, we cannot, of course, but if you can see inside, you will see something very sharp, not like this, but just slightly bended, okay? So how does it work? It works that the electrons which are incident in the lens hole with higher angles, so that are more deflected from the axis, will be deflected more than the electrons which are more close, passing more close to the center. And in this way, I have a focusing effect. Okay, so I can collect all the electrons in a point at the focal length. There are several different lenses inside the column. And at the end, where the sample is here, you have a focused beam of a few nanometer size. And then, of course, we need the detectors, because after the interaction between the beam and the sample, I want to detect the signals. And very first important signal that I'm going to speak you is the secondary electrons. Secondary electrons, I will tell you in a few minutes what they are. There is a detector here inside which collect the secondary electrons. These secondary electrons are typically electrons of with low kinetic energy, let's say from 0 to 50 eV, from 0 to 50 electron volt. So I can drive the electrons, which are at low kinetic energy, toward a scintillator. Then there is an optical waveguide, and then there is a photomultiplier tube, typically. Okay, this is the standard secondary electron detector, which can amplify the signal and so count the intensity of the secondary emission. There is another very important kind of detectors, which are the backscattered detectors. In this case, a completely different situation. We have a silicon PN junction, let's say, silicon diode, which can convert the incident electrons, in this case with higher energy. Backscattered electrons have an energy of at least 100 eV, but can go up to several kilovolts. Okay, and they convert the intensity of the backscattered incident electrons into a current, and then this current is proportional, let's say, to the intensity of backscattered emission. These kind of detectors are typically placed, so you see a hole here, because this is the hole where the beam is passing through, and they are placed just right below the exit aperture of the electron beam. So here, for example, the beam passes through the hole, they interact, and they collect the backscattered intensity. Okay. Also, in our case, I will show you later, the backscattered is exactly in this situation. Okay, so let's say something about what happens when an incident beam of electrons at some kilowatt of energy is incident on the sample. What happens? What is the kind of interaction? The first, okay, as I said, we have different signals, either electrons or light, and let's start with the electrons. If I measure the spectrum in energy of the electrons which are coming out of the sample after the interaction, I will see something like this. So I have Okay, if these are these are the elastically reflected electrons. In this case, the energy is the same of the incident beam. For example, if we have a beam at 10 kilovolt, the elastically reflected electrons are also at 10 kilovolts. Okay, these are so-called elastically backscattered. Then, of course, I have backscattered electrons in a wide range of energies, because some of them lose some energy after the interaction. And then I have a big tail of secondary electrons. Typically, the secondary are defined as between 0 and 50. This is not a sharp number. You can also have 70 or something like this. But anyway, let's say in the low energy region, you have secondary electrons, and then we will see what they are. And we have also Auger electrons. Let's go step by step. So what happens when the incident beam is coming inside the sample? This is a Monte Carlo simulation of a beam of electrons at 30 kilovolt. How they propagate, what are the trajectories inside a sample of iron, for example. Okay, and you see that the electrons, as soon as they come inside the sample, they start to diffuse in a trajectory. Okay, and in these trajectories, you can see that there are some small deviation, but also some sharp deviation, like here, for example, some kinks. Okay, why? Because there are mainly two things that a high energy electron can experience inside the sample. He can experience interaction with other electrons. Okay, in this case, they experience energy loss. They decrease the kinetic energy, but typically the deviation angles in this case are small. Okay, so for example, here you can see many small deviation angles. So these are all interaction with the electron. And then you see also some other kind of deviation with high angle. These are typically because electrons can also interact with the nuclei in the sample. In this case, they don't lose much energy, but they can have large deviation. Okay, and these are the typical trajectory of the electrons inside the sample. How big is this region where the trajectories of the electrons are included? These depend on the beam energy and on the material. This is also called the interaction volume. This is a very important concept that you have to understand if you want to understand how to read the SEM data. Okay, the interaction volume is defined as the volume which include, let's say, the 90% or 95%, depending on the books, of the trajectory of the electrons. Okay, and as I said, this interaction volume depends on the material and on the beam energy. On the material, here you can see, for example, what happens if you have an incident beam at 20 kilovolt in carbon, in iron, in silver, and in uranium. These are four elements with very different Z. Okay. There is a question. I saw something. Sorry, but I cannot.
Professor, we can take questions at the last. No problem, sir. You can continue.
Sorry.
Yeah, I was saying we can take questions at the last. You can continue, sir.
Okay. Sorry. So let me continue. Okay, so here you can see that, for example, in carbon at 20 kilovolt, you have an interaction volume of several micrometers. Okay, let's say 5 micrometers. While in uranium, with the same beam energy, we have an interaction volume of maybe half a micrometer. Okay, so the highest is the Z, the heaviest is the element, the lower is the interaction volume. But of course, it depends also on the beam energy. Here in iron, we see the difference between 10, 20, and 30 kilovolt. You can see that at 10, we have an interaction volume of half micron, even less, while at 30, we have an interaction volume of 3, maybe, micrometer. Okay. The Kanaya-Okayama relationship, which is this, which will tell you how much is the so-called electron range or interaction volume. Okay? And as you can see, it depends on A, atomic number, Z, atomic number, atomic mass, A, and very important, also the density of the material, and of course the energy of the beam. Okay? So if you want to understand where your signal is coming from, you have to consider, first of all, how big is the interaction volume. The second thing that you have to consider is how much the electrons of your signal can travel inside your sample. This is also very important. Because, for example, you see in this picture that, for example, if you have an interaction volume of a few micrometers, let's say 1 micrometer to be easy, okay? But so in all the interaction volume, you generate the secondary electrons. But only the secondary electrons which are generated very close to the surface can escape and reach the detector. The secondary electrons which are generated here, they are there, but they will not reach the detector, so they are not visible. Okay. This curve that you see here is the inelastic mean free path in the solid matter, let's say, okay, of electrons. And you can see that in a range of, for example, the secondary electrons we said are, let's say, few tens of eV. Okay, so 10, 20, 50, something like this. In this range of energy, the inelastic mean free path is less than 1 nanometer. This is in angstrom. Okay, so they can travel really a small distance inside the sample before being absorbed. Okay, so they will not reach the detector if they are generated here, but only if they are generated, let's say, here. Okay. So, as I said, out of this interaction that we tried to describe very briefly, we have 3 kinds of electrons: the secondaries, the backscattered, and the Auger. Secondaries are this, Auger are these, I will speak a bit about later, and the backscattered are all these electrons from elastically to, let's say, 50, 100 eV. Okay. Let's go briefly through what they are. Secondary electrons are the electrons which are inside the sample and which are excited by the interaction with the electron beam and which have enough energy and they are enough close to the surface to escape the sample surface. Okay. As we said, these are generated, typically, the one that I can detect are generated very close to the source. So these are very surface sensitive signals, okay, the secondary. What are the source of contrast in the, so if I plot the secondary electron emission, I have an image, for example, like this that I show you here, okay? What are the sources of contrast in a secondary electron image? First of all, the local surface orientation. And this is, I can show you this picture, okay? And here you can see that the part of the interaction volume, which is close enough to the surface to allow for emission of secondary electrons, depend on the local tilt of the surface. If I have a flat surface, the volume which can emit the secondary is very small. While if I have a locally tilted surface, the number of secondary electrons which can escape the surface is much higher. For that reason, we say that secondary electron emission is dependent on the local surface orientation. And here you can see that This is very important factor, because this means that all the edges of the features that you see in your image are brighter than the part which are not close to the edge. Also, on the very small features, like for example, you see each of these grains it has a bright edge, and this is exactly because of this effect. So at the edge, or where I have a tip, for example, I have a larger emission of secondary, and these highlight the edge of the features, which is very useful if you want to know the morphology of your samples. Another important factor which affect the contrast, so which is a source of contrast in the secondary electron image, is the shadow effect. What does it mean? It means that in this case you have to consider where is the secondary electron detector in your system. For example, in this microscope, the secondary electron detector is in this position, so at this side, let's say, of the image. Okay, and it happens that depending on the position of the detector, in some regions it will be easy for the secondary electron to be driven toward the detector, while in other positions, for example here or here, that I have a hole, or here, the trajectory of the secondary electron when they are out of the sample in order to reach the detector will be much more difficult. Okay, and so it will be the detected signal will be lower. So you will have a bright area, the one that are facing the detector. There will be less bright area. These are areas which can still be excited by the beam, but the travel toward the detector is difficult. And then I have not visible areas, which are the ones which are not illuminated by not irradiated by the electron. And for that reason, for example, this part of this feature is brighter, while this is darker, and so on. Okay. There is a third factor which affects the emission, the detection of the secondary electrons, which is the local Ward function. And oh, sorry, yeah. Yes, this is worth to say. This source of contrast called shadow effect give a kind of a 3D vision, let's say, of the sample surface. This is very interesting because it help the microscopist in having a three-dimensional view of the surface. Okay, because somehow you can mimic the same situation if you have a light source and an observator. Of course, the light source is in the place of the detector, and the observator is in the place of the beam. Okay, and so this shadow effect help. Of course, it is not like you have a light source and an observer, but it mimics somehow the situation in which you have an illumination from this direction and you are watching the surface from top. Okay, it is only a side effect, but it is very useful for 3D representation in your imagination of what is the morphology of the surface. And okay, there is also a third source of contrast, which I call here local Ward function. Is not exact description. Is not only the Ward function, but also all the things which can affect the emission of low energy electrons, which can be the local charge, the material. Okay, metals typically are a bit brighter than insulators, and so on. Okay. These are the secondary electrons, and these are very much used for morphology analysis of your sample surface. And another very common signal is the backscattered electrons. Very important. Here, so what are the backscattered electrons? These are the electron beam, the electrons which were in the primary beam, so incident beam, which after some scattering are escaping the surface. So these are these lines that you see here. are the backscattered electrons. So they can have an energy also of some kilowatt, okay? And what is the main source of contrast in the backscattered electrons? This is the local density Z, okay? So the higher is the atomic number, the higher is the backscattered coefficient. And here we see a nice example of this. This is a sample, polished sample of a ceramic, of a fluorescent ceramic, okay? And here in the bottom, we can see a backscattered electron image. And we see that we have some brighter area and some darker area, okay? These are areas without a different in the morphology because the sample is flat here, okay? But the contrast here is given by the different elements, the different composition which is there. And also these are different phases of the material, of the ceramic material, okay? So depending, of course, the high density phase will be brighter and the low density phase will be darker. If I take a secondary electron image of the same sample, I will not see much contrast. I will see some contrast, also because in the secondary detector, also some backscattered gets in. But anyway, here the morphology is much less important, and I will see very small contrast between the phases, okay, in the set, while I have a very nice contrast in the backscatter. Here you can see another example of the difference between secondary and backscattered. This is a magnet which is used for automotive industry, and in this magnet we have iron and rare earth rich domains, and in the backscattered electrons we can easily distinguish the phases which are rich in rare earth, which are heavy element, and the rest of the material which is iron. So in this case, the iron is the light material because it's lighter than the rare earth, okay? If we take the same picture with the secondary electrons, we will see, first of all, no difference between the phases. I cannot see the different phases. But I'm much more sensitive to the surface feature, okay? And in particular here, you can see this giraffe-like pattern. This is given by a surface contamination. This means that after polishing, I left some carbon contamination on top of the magnet surface, okay? And I can see it very well. While this is just few nanometer of carbon, I cannot see at all in the backscattered electron. These few nanometers of carbon are invisible in the backscatter, but I can see very well in the secondary. For that reason that I told you before, that the secondary emission is also affected by the local work function. So if I have some change, for example, I have some carbon contamination, in that point, the emission of a secondary is lower because it's somehow non-conductive part of the sample, okay? Only at the very top. So I can see this difference only in the secondary. Okay, and this is a last example of a multi-phase bismuth iron vanadium oxide. This is a secondary electrons, and this is very good to see the morphology of the material, okay? But it's not useful if I want to distinguish the different phases. While this is the backscattered electron image of the same sample, okay? And you can see secondary, backscattered. In the backscattered, I can easily distinguish between one phase and the other phase because they have different density and different Z, and so they have different contrast in the backscattered electrons. Okay, before continuing, I will do a very small break, and I will be back in 1 minute, okay? Sorry. Okay, I'm back. Since I'm a bit short in time, I will skip for the moment the Auger electrons, also because this is much less common signal to be detected in the microscopy, because you need an energy electron analyzer, which is not a common attachment in a SEM. In some cases you have, but it's not common. So let me skip this and give you just few info about the sample preparation. This is also very important. So in some cases, you need to prepare your sample, otherwise you cannot watch it in the microscope. And here, this is the sample preparation room, which is just beside this lab. And here we see some typical piece of equipment. For example, a wire saw, cut the samples, a cross-section polisher, a etching and coating system, this, and okay, this is only for TEM, ion beam polisher. Now I will mention you this, the etching and coating system, and the cross-section polisher. These are the two machines which are typically used to prepare sample for SEM. What are, well, the first, the etching and coating system. This machine is used to produce a small coating of conductive material on top of your surface. Because if your material is not conductive, you will charge typically the current, the incident current of the incident beam is not equal to the number of electrons which are going out of your sample, either backscattered or secondary. It's only in very specific situation they balance each other, but typically they are not the same. And so it happens that after you start your measurement, you charge up your sample. Okay, and these, of course, greatly affect, especially the secondary electron imaging, because secondary electrons, as we said, have low energy and they can easily be affected by local field or charge on top of the sample. Okay, so you will not do any secondary electron image if the sample charge. And so if the sample is not conductive, you have to coat it with some carbon or some metals. And for example, here I show you, this is a neuronal cell on top of some polymer substrate. Now, in order to watch this kind of systems, besides the fact that if it is a bio system, you have also to dehydrate and fix the sample, okay? But this is something that I will not go through because this is only for biological sample. Typically, you don't do this for material science. But anyway, after this, you have also to coat the sample with some metal or some carbon in order to make it conductive. Otherwise, you cannot watch. And these are the images after coating of with, in this case, it was platinum. And another very important sample preparation technique, which I want to mention, is the cross-section polishing. In several cases, you need to analyze a sample in cross-section. And well, if it is easy to cleave it and have a flat cross-section, you can also do it mechanically. But sometimes it's not easy, and you want a very precise and flat cross-section. And so you use this machine, which with an argon ion beam, mill the sample and polish very carefully your material. And for example, this is a IC circuit, an integrated circuit, and this is after the cross-section polishing. So this is a side view, okay? This is the silicon. This is the, no, sorry, this is the silicon. This is the silver paste. This is the plastic substrate. This is the top part of the IC, the black part, okay, which is insulator. And here you have the real IC part, okay? So the part with the transistors and contacts and so on. And so if you want to image that part, this is the cross-section polished by argon ion milling, this, let's say, shape, V shape, okay? If you watch closer, you will see this is the insulating case, this is the silicon, this is the nanostructural part. And if you watch closer again, you will see this. So this is this part, okay? And if you do it properly, you have a very high resolution and you can image the details of the IC circuit down to a resolution of a few nanometers, okay? But to have this, you have to do a cross-section polishing very, very flat, okay? Otherwise you cannot. And then you can also do EDX to understand which elements are there, but this I will explain you later. Okay? Okay, so now I would like to, after so much speaking, I would like to show you something live. Of course, it is not like to have you here, but I can try to give you a feeling of what is a typical SCM session, okay? So the sample that I am going to show you is a thin film of a nanostructured thin film of silver together with the titanium dioxide, which is deposited. This is a collaboration with Italy. We just published the paper a few months ago, and they want to know, they send me two samples with the same film after thermal treatment, one on sapphire, alumina, and one on silicon oxide. And they asked me to analyze what is the distribution of silver after the thermal treatment that they did, okay? So after I received the samples, I did a coat, since these are not conductive samples, I did a coating of 6 nanometer of carbon, and then I mounted, and now I try to show you what they are. So, just before starting, what is the typical layout? What is the typical, let's say, routine in a SCM session? Of course, the first important thing is have a question and an hypothesis clear in your mind. Don't start just watching your sample like this. Then prepare and mount your sample properly. And in particular, you have to care about three things. One is that the sample will not move or fall down or vibrate inside during the measurement and inside the chamber. Okay. And the other thing is if the sample is conductive or not, if the surface will charge up or not. And in this case, I did the coating exactly to avoid charging. Okay. So now I will mount the sample. This is the table. So this is a sample. I already mounted it. These are the two samples. As I said, one is on silicon oxide and one is on sapphire. I mounted the two wafers on top of a glass and I fixed it with the carbon tape. Carbon tape is double-sided tape made of carbon. Okay. It's conductive and compatible with UHV, so vacuum. And so I already put the carbon tape around, and now I can fix it on the sample holder. This is the sample holder. I stick it with the carbon tape. I add some carbon tape on the side.
Mattia, if you stop sharing, you will be on the bigger screen.
Oh, sorry.
That's much better now.
Sorry. So I just fixed with the carbon tape the sample on the sample holder. And so can you see the two samples? Yes. Okay. And now I put some additional carbon tape in the side in order to ground the sample surface the sample holder body, okay, in order that the current can easily flow from the sample surface toward the ground of the system. Okay. Okay. Now I already know who is who, but typically when you mount more than one sample, you draw a map of your sample in order that then you can recover the position when you have when you watch it with the microscope. So now I will mount the sample holder with the sample on top in the machine. Let's go here. Okay, this is my sample. Now, this is the load lock. This is a compensation chamber in order that to insert something in the vacuum, I will not have to vent all the system, which is not convenient because then it takes a long time to recover the vacuum. I will only vent this small part. Okay. Now I will let nitrogen flow inside only this part. Can you see? Yes. Okay. This is the transfer arm. Okay. Now I mount my sample here. You see? Now I mounted the sample and I close. And now I make the vacuum again here. When the vacuum is done, the valve inside here will open and I can insert the sample inside the main chamber. This is the typical view inside the just a bit. Okay. This now I show you what is inside the chamber. This is a camera view. The camera is on the side of the microscope in the vacuum. And here you can see this is the end part of the column. So the last lens, the objective lens, and the aperture out of which the beam is coming out. Now the beam is not coming out because there is a valve here in the middle of the column, which is now closed, which separates the gun and the sample chamber. So the gun is protected by the, let's say, because the gun is the one that require the higher vacuum, the best vacuum, okay? After I will be ready with the sample in position, I will open this valve and the beam will be incident coming out here and be incident on the sample. Now I insert the sample on the stage. Okay. Okay. Now the system is asking me how thick is the sample. I write 3 millimeter for safety reason. He asked me. He doesn't want that I will crash the sample against something. Okay. And now I can
now you see that the vacuum in the main chamber is recovering. I have to wait until I am in a low -4 Pascal regime. In the meantime that I wait for the vacuum, I can put the position for the sample and decide which energy of electron beam to use and which current and so on. So first of all, I put the sample in close position to the column. Okay, so this is the sample. This is the sample holder. Now, since these silver particles that I'm going to analyze are pretty small, I will go to quite close working distance in order to have a higher resolution. Here, of course, with the experience, you will understand which energy to use, which working distance to use, which current, and so on. Now, of course, today I cannot explain you all these things. So I'm just telling you that I'm going to use a 15 kilovolt. I go pretty close, okay, like this. And I put a probe current 9, that's fine. Okay, now I have to wait for the vacuum to be ready. Okay. In the meantime, I explain you a few things. This is, as I said, the end part of the column. This is the sample. Here we see kind of a microphone. This kind of a microphone is the secondary electron detector. Okay, it's a grid which is at plus 300 volt, which attract and collect the secondary electrons which are emitted by the sample. And here there is the scintillator and the photomultiplier. So, on contrary, this that now I will put in back again is the EDX detector, which is retractable. And it is for EDX. Maybe later I will show you an example. For the moment, I didn't explain you yet. Okay, this is the EDX detector. And then we have also a backscattered detector, which is retractable. And I will insert it in a while before I have to align. So the first thing to do when you start a measurement is to align the beam. And so now I will briefly do it. So now I open the valve and I watch around to see what is the situation. Okay, I go. What happened? Just a second. I have a very low signal for some reason, which I don't understand. Okay, it seems that the secondary electron detector has some problem. But I tried it 1 hour ago and it was working. So I don't know exactly what's going on. Okay, let's try with the backscattered then. So now I insert the backscattered electron detector, which is here on the side. Okay, this is the backscattered electron detector. As I told you, it is just below the hole of the gun. So there is a, okay, here you see only from the side, the image I showed you before. There is a hole in the middle, then this diode will collect the current of the backscatter. Let's try if the backscatter it works. Yes. We are a bit unlucky today. It doesn't work. Okay, here we have a problem, quite serious. And probably for some reason, the microscope is not aligned. Some big misalignment happened. And so we are completely out of alignment. Ah, here. Someone moved to the aperture. Sorry. Okay. Here we are. Okay. Okay. Now I can see what is the situation. Okay. Sorry for inconvenience, but now I find out that the aperture was moved. Now it's back. Okay. So first of all, let's find the sample. This is the carbon tape. Sample. Now we have to find a small feature to get aligned. Okay. Now just be patient 1 more minute that I perform the alignment. Okay. Now I have to set the stigma. The stigma are the correction to the shape of the beam, because the beam maybe is not perfectly round, the section, let's say. So I need to correct the estimation. This is also something quite fast that I can do in 2 seconds. Okay. Okay, now we are almost there. Let's try to focus a bit better here. Okay. Can you see? Yes, something?
Yes, sir. It's blurry. Still it's blurry.
Yeah, now then I will show you the images that I collected so you get a better idea of the sample. For the moment, just, okay. Now I did the alignment and the stigma correction, okay. Now this is the sample on the silicon oxide. The film is made of, as I said, of titanium clusters and silver clusters. And after some thermal treatment that, okay, I don't give you all the details. If you want, you can read the paper. After some thermal treatment, the silver cluster got change a bit the morphology. So this is the secondary electron image, okay. And now I can improve a bit the contrast, okay. So this is what you can get. You can see after rough alignment with the secondary electron image. It's a bit drifting because I mounted it a bit faster, but anyway, this is what you can achieve. Now I go slower. And this is the typical image that you can see in the secondary electron. So secondary electrons, as we said, are very sensitive to the surface feature. You can see very well the holes in the film. There's some small bright dots, okay? Some bigger dots, okay, here. So, of course, you have to consider that this is coated with the 6 nanometer of carbon. So this makes the morphology a bit different, but not much, just 6 nanometer. So how big are these clusters that I see here? So if these are 100 nanometer, these small clusters are, okay, let's use this. Yeah. So this, for example, this small cluster is 17 nanometer, this one, okay? And there are also smaller clusters. And now we are at 15 kilovolt, not at the highest possible resolution, okay? So we have a resolution, let's say, of few nanometer, okay? This is, for example, 11 nanometer, okay? Okay, this is what we can see with the secondary. Now let's see what we can see with the backscattered. We can also run the two maps in parallel if we want. Now I show you, for example. Now here I have the secondary, and now here I put the backscatter. Okay, so these are the two signals collected in parallel. Okay, now I will acquire a picture, a bit more counted, so you can see the difference. Okay, let's regulate a bit better the contrast. Okay. Now I can show you a picture. Okay. Here you see that I'm changing the speed of collection, which change the integration time. And so if I go slower, like I'm doing now, I have more integration time in each point. Of course, it takes longer to take a picture, but on the other side, I have a better signal to noise ratio, While if I go faster, it's more comfortable to go around, but of course, the image is more noisy, okay? And now this is the result. Now I save the image. There you go. Okay. And now I show you the two images. This is the secondary, this is the backscatter. So you see, there is a difference because, for example, here you see this. Okay, let's go. This is the backscatter. Here you see these bright dots. These are the silver nanoparticles. Also the small one are the silver. Sometimes they are on top, and so I can easily see them also in the secondary, like this. But sometimes they are inside the film, and in the secondary, which are also sensitive, they are invisible. For example, here or here. You see some signal brighter, but this is because in the secondary I have also some backscattered electron, but I cannot really see much here, no? But if I watch with the backscattered, you see clearly that here below there is a cluster, for example, okay, of silver. Okay, now this is just a fast demonstration, so just to give you the feeling of what happens when you do SEM. Of course, a SEM session can take also several hours, depending on how difficult is the sample and how complex is the analysis that you want to perform. Now, I will stop for a while here. I'm sorry for the inconvenience of the detector, but it was something unexpected. But now I'm happy that it got resolved. And okay, now I will go back a bit on the presentation because I want to explain you a few other things. And also I will leave you some time for the questions. Okay, let me share again the presentation. Okay. So as I said, when you start doing your session, you have to select the correct parameters, the energy, the current, the working distance, then align the stigmators, align the beam, focus the beam, of course, and then you can start to collect your pictures. Okay, these I will skip for a while. And these are two images that I collected on the same sample that you just saw, that we just measured. This is the secondary, and this is the backscattered. You see the difference? As I was saying, in the secondary, you are more sensitive to the surface morphology. In the backscattered, you see the composition. For example, this silver cluster is below the surface, is not visible in the secondary, but you can see it in the backscatter. Okay, let's go on. Now, in the last part of my lecture, I would like to tell you something about EDX, very important technique, also called the microanalysis, or EDX. It means energy dispersive X-ray spectroscopy. So EDX is a powerful tool to do analysis of the elemental composition of your sample. So to understand which elements are there and possibly also how much of them are there. Okay. The detector is again, you saw it before. So let's just briefly say why atoms, after being excited by an electron beam, are emitting X-rays. This is because of the so-called phenomenon of fluorescence, which happens like this. These are the incident electrons. They can ionize atoms. It means that they can scatter with electrons in the inner shells, in the core level of the atom. Okay, so they can create a hole, and this is, of course, a non-stable situation for the atom to be, with a hole in the core levels. And so what can happen is that the situation relaxes by the emission of an X-ray. And in particular, it means that an electron from an outer shell will go to replace the electron in the inner shell, which has been ionized, and the excess energy is released in the form of a photon, high energy photon, in particular, so that we call an X-ray. Okay, so this energy, so the energy of the photon, depend only on the energy levels of the atom. So each element have different fluorescent emission lines. Okay, depending on how many shells they will have even more than one, of course, emission line. So, for example, zinc has a K series. The K and the L names are given regarding which is the what is the shell of the first hole. No, so what is the ionized shell? Okay, so you have K lines, L lines, M lines, and so on. And each element have a very sharp emission line, which are typical of that element. So if you have a detector which allow you to measure what is the energy of the photons which are coming out of your sample, you can understand what are the elements in your sample. I remind you what I told you before, that if this is the interaction volume, in the case of X-rays, they can travel several micrometers inside the sample before being absorbed. And so actually the part of the sample which you analyze by EDX is much larger than the part of the sample that you collect the signal, for example, in the case of electrons, okay, of the secondary electron. So the lateral resolution in the case of EDX is much smaller. It's much worse, let's say. You have a resolution of at least 100 nanometer, but even more, okay, typically. So if you have an analyzer of the photon energy, you can collect a spectrum, which is nothing else than an histogram, where you plot how many photons you collect for each energy. Okay, so this is an EDX spectrum. And if you watch the spectrum, you will see that, okay, there is a continuum, a background, and then some very sharp peaks. These peaks are the typical core level, sorry, the typical emission lines of that elements which are in your sample. For example, in this case, silicon, arsenic, and gallium. Okay. I will skip this. Okay, if you want, you can also measure the intensity of these peaks and understand how much of these elements are inside your sample. And of course, to do this, you have first of all to measure the intensity of the peaks, but then you have to consider that several factors can affect the intensity of your peaks. First of all, which elements are there and what is the beam energy, because these influence the cross-section of the fluorescence process. Of course, then you have also to consider how many of these X-rays which are emitted are absorbed by the rest of the sample during their travel to the detector, and also that some atoms can absorb the X-ray emitted and again emit by themselves other X-rays. This is the so-called fluorescence factor. Inside the software which analyzes the spectra, typically you have already some standards, is already calibrated in order that you can run a routine which try to take into account all these different effects and give you some numbers, you see here, for the different elements. No? So he measured the intensity and he do some calculation and it give out these numbers. Of course, these numbers are the product of a quite complex calculation and are only valid if the hypothesis on which the calculation is made are correct. No? And in particular, what are these conditions? That the sample is flat, polished, that the sample is homogeneous in Z, and
so laterally, and that the sample is stable under the V. If these three conditions are met, then the quantification is pretty reliable. Okay. If they are not met, so if the sample is not flat, not homogeneous, and so on, then these numbers can be also very wrong. So be careful about this. Okay, these are the different things which can affect the X-rays emission. Okay, so what are the two principal modes of analysis that you can use your EDX apparatus? One is the collection of a spectrum in a single point or in a region, and then the analysis of the elements. So which elements are there, how much, okay, the concentration. The second thing that you can do is to do a map. A map is something like this. For example, this is the same magnet that I showed you before. And you can say, you can decide to map, to plot the intensity at a given emission line. For example, this is the map in this region of the iron K alpha 1 emission line. Or this is the map of the neodymium L alpha 1 emission line, and so on. So you can see what is the distribution in your area of the different elements. You can also, after you collect the different maps, you can also overlap them and make something like this. No, in this case, this is a mechanical part, and you can make a layered image where you have iron, for example, carbon and copper. You can see how they are distributed around the sample. Or, for example, this is a rock sample. And here you can analyze what are the different phases inside the rock. And this is the same sample that we were watching now. This is the on silica, the one that we actually imaged. This is the other one. And these are two images, two maps of the silver emission line out of these two regions. And by doing these maps, you can understand, for example, in this case, that these you have the proof that these clusters are made of silver, okay? And you can understand what is the distribution of the silver, in this case, over your surface. Or, for example, in this case, you can see that you can also measure the spectrum here and see that if you have silver also left in this part or not, and you can answer this question. Finally, I tell you that this book is one of the books that I feel to suggest, especially for microanalysis, but also for imaging, which is a kind of very famous book for SEM and EDX. Of course, there are also others. Okay, so now, what's the time? Okay, now I think that I will skip cathodoluminescence because of time restriction, and I will leave some time for questions. And so I suggest that now we do 2 minutes of a break, and then I'm available for question and answer session. And then if some time is left, I will also show you the EDX acquisition. Okay. So see you in a couple of minutes.
Thank you, Professor. So participants will be having 2 minute break. So meanwhile, if any one of you have any question, you can type it in the chat box or you can raise your hand. We'll unmute you for a while. So thank you. You can also post it in the question answer section. Or if you want to ask directly, you can raise your hand. So we'll be here back in 2 minutes. You can ask your questions then.
Okay, so let's see some questions.
So we
Hello,
have few
everyone.
questions in the chat box. We have few questions in the chat box. If you can.
Yeah. I can see them. Yes. So why a high vacuum is required in lanthanum hexaborite, Schottky, and cold FeG as compared to tungsten? No, well, high vacuum is required in well, I would say all of them, mostly because the filament is typically heat up at a high temperature, and sorry, at a high temperature, and if you don't have a good vacuum, the filament lifetime will be very short. No, well, it is true that depending on the temperature, let's see how much is the temperature exactly. Now I share again the screen. Okay, so the tungsten is kept at 2700. You understand that if you don't have a high vacuum, tungsten will blow in a few seconds. Okay, so the best is the vacuum, the longer is the lifetime. It is true that in the old SCMs, in particular the ones that are not required for a very high resolution, the tungsten tip is somehow economy solution, no? For the microscopes which are meant to work with a bit less resolution and maybe high current. Okay, so this is a kind of a economy solution, and the resolution is also much lower in the tungsten case, typically maybe 20 nanometer resolution, even more. And so anyway, the vacuum is required for that. For the other two, vacuum, of course, is also required in order to, especially in the case of field emission, in order to preserve the filament, but not only for this. Also, to avoid scattering of the electrons in the beam with the molecules of the atmosphere, right? Because the beam which is coming out of the filament and out of the anode assembly, let's say, is monochromatic as much as possible, and also coherent and spatially confined. Okay, so if you have molecules of atmosphere around which can scatter with the electrons, you will spoil the characteristic of your beam, and so decrease a lot of the resolution. The only filament which is kept not high temperature is the so-called cold field emission gun, which is similar to the field emission gun thermal, Schottky, but is not heat up. In this case, you don't need to heat up, you just rely on the high curvature and the strong field at the tip. And why they use a cold emitter? Because in this case, the beam is even more monochromatic, because you don't even have the thermal broadening of the energy of the beam, of the electrons, okay? And this is required if you do some particular spectroscopy where you need very monochromatic electron beam. In this case, of course, you don't have the problem of the oxidation of the filament, but of course, if you want to be so monochromatic in the energy, it is obvious that any scattering with other molecules will spoil the characteristic of your beam. So also for that reason, you need the vacuum. Let's see. Another question. If something is not clear, tell me. Okay. Why we always use carbon black tape? Why no other side tape can be used? Okay. Carbon tape has three very nice characteristics. One is double-sided. Okay. Second is UHV compatible, very important, because if you use a normal tape, maybe when you go in vacuum, it will outgas some gas or some substance which spoil your vacuum, but carbon tape, at least at room temperature, is very stable in vacuum. And the second and the third, sorry, is that carbon tape is conductive, so you can use it very effectively to ground the sample. Now, I don't know if there are other double-sided tape with the same characteristic, and also carbon tape is not that expensive, so you can find it. So I don't know if there are other solutions, but this is by far the most common solution, very, very useful and very practical. Then this is what I can tell you. So anyway, it has to be conductive, vacuum compatible, and double-sided. Then if you have these three, it's fine. Now, another question is, can we detect functional groups using EDX, such as in MXin or reduced graphene oxide? Okay, good question. As I said, the signal coming from EDX is coming from a big volume of, let's say, some 100 nanometer up to few micrometer wide interaction volume. So first thing to consider is how thick is your layer. If the layer that you want to analyze is too thin, then the signal will be too weak with respect of the emission from the rest of the interaction volume to be detected, okay? Okay, this is a first thing. Second, what material you have there? If it is carbon, carbon has only one K line at pretty low energy, which means 0.3, roughly 0.3 kilovolt. And the fluorescence for let's say for light material, EDX is not that effective. Much better would be Auger. Auger cross section is high at low Z. So light material like oxygen, carbon, nitrogen, and so on have a very good Auger emission, but very low EDX, and vice versa. If you go high with the Z, you have better X-ray emission and lower Auger, okay, in general. Now, carbon typically is, okay, you can detect, of course, the carbon line, but if the sample is if the film is very thin, the signal will be very weak. And the third thing that is very important, EDX is only sensitive to elements, but not to chemistry. So you can detect maybe that there is a carbon, but you cannot know what is the chemical environment of that carbon. So you cannot understand by EDX if the carbon is bound to oxygen or to hydrogen or to nitrogen or whatever else, okay? So this is a very important point. While in Auger or in XPS or also in WDS, which is EDX but with a very high resolution, okay, then you can also distinguish the chemistry. But in standard EDX, the chemistry you cannot understand. You can only understand which elements are there, but not which chemical species, how they are bound to other atoms, okay? So reduced graphene oxide, if you watch some graphene oxide, you will see maybe if it is thick enough and if your system is sensitive enough, you will see some carbon and some oxygen. But that's it. Forget to measure the stoichiometry or and also the problem is that oxygen and carbon are always on a surface. Typically 95% of the time you have some carbon and some oxygen on top of your sample. So because of contamination. And so the graphene oxide will become, I wouldn't use EDX to study graphene oxide. For MXin, well, depend on what you have inside.
For example, I think you have titanium sometimes, or I'm not very expert about this, but I think you can have some titanium inside or some other metals. Then yes, actually with this microscope, they are doing some analysis of MXene layers. They can catch the metal signal. They can study a bit how they are distributed on top of the surface. Yes, you can do it. The signal, if the flakes are not very thin, let's say, if the flakes are very thin, the signal will be weak. But if you have time to count, then you can do it. Yes, why not? And last question is there any characterization technique for studying live behavior of high temperature materials? Oh, this is a very nice question. Because typically in SEM, you do not have the capability to heat up the samples unless you don't have a heating stage. And this laboratory is the only one that I know which have a heating stage for SEM. Probably there are also others in the world, but it is really not a common thing. So you need a heating stage. I can show you exactly what I'm speaking about. Okay, these are, let's see if I can show you. Let's break it. This is a heating stage for SEM. So it is a stage, an object that you can mount inside of, in this case, you cannot use the load lock to mount the sample. You have to open the side wall of the microscope, but it's not something, it's something that you can do. And you can mount this object inside the microscope. And in this object, there is a housing for the sample. Okay, here you can mount the sample inside the heating stage. Then you mount inside. You connect it with these cables. There is also water cooling. You connect it to the external flange of the microscope. So here you can see this flange. This is the connection to the heating stage. So this is the water pipes. No, these, sorry, are the water pipes for cooling. These are the wire to give power to the heating. Okay, this is the heating stage controller, the power supply. And then there, that box is the water chiller, no? Because if you go too high with the temperature, you need the water cooling. Otherwise, you don't need it. Okay. And by this, you can heat up the sample directly in the chamber and observe what happens at high temperature. This heating stage can go up to 800 Celsius. The use of the heating stage requires some care, because when you go to high temperature inside SEM, you can destroy many things. First of all, the detectors and also other things. So you have to be very careful. But in principle, you can do 800. I've never done until now, but 500, for example, you can easily go. Yes. Okay, let's go for another. What are the factors that can affect the EDX data? Atomic percentage, or it is always true? No, the quantification given by the software is, I would say, only in specific situation is reliable. Okay, let me share again the screen. Share again the screen. The EDX. Second. Okay. So what are the factors which affect questo? Okay, let's go step by step. First of all, what is the probability that an atom is ionized and then that it decay, that it relax by emitting a photon, okay? The ionization cross-section tell you what is the probability that an atom get ionized by electrons in the incident, okay? And as you can see, this is the over voltage. So the ratio between the incident beam and the energy of the core level, okay? Of course, if you have an incident beam which is below the ionization cut, you have zero probability. Then it starts, and it has a maximum at about 5 times so if you are, for example, studying the oxygen emission, which is at the edge of absorption is at half a kilovolt, you will have the maximum of the ionization cross-section at about 5 times, so 2.5 kilovolt. And then, of course, so this depends on the beam energy, okay? And the maximum is typically about 5. But it's not say that if you go higher, you don't have any ionization. You still have a bit less, but you can also go higher, okay? Important is that you are not below, let's say, 2 or typically 2-3 times more than the emission lines energy that you want to analyze is better to be. Okay, so if you are watching, I don't know, silicon, no, silicon, let's say iron has a line at 6, stay at least at 15. Otherwise, okay, you have an emission of ionization even at lower than 15, but it will be not much effective, no, the ionization. Second, what is the probability that an ionized atom decay emitting an X-ray? And this depends on the atom. As I said, the higher you go with the Z, the higher is the probability for an X-ray emission. And the smallest is the probability of the Auger transition, and vice versa. Then you have to consider also many other factors. What is the probability once you emit your X-ray? What is the probability then the X-ray get absorbed during the travel toward the detector? This depends again. This is the so-called absorption factor in the ZAF matrix. The A is the absorption, so which consider how much of these X-rays are reabsorbed by the material itself. Okay. And also, what is the probability that an atom which absorb the X-rays again emit another X-ray because of fluorescence? This is typically a bit less important factor. The F factor is a bit less important, but still you have to consider it. No? And so you see here, I'll try to show you better. Okay, here, after you collect a spectrum, okay, the first thing is to understand what is the intensity of the peaks. Okay, so you have to subtract the background and to measure the area of the peaks. Okay, but then this is only the first step. Then you have to understand which elements are there, and according to this, you try to understand which Z, A, and F factor are important to put in your matrix, in your correction matrix, to understand what is the concentration of the elements, but each, and then after the first routine, you will use the result of the concentration again for new Z, A, and F factors. No? So it's a loop, it's a routine. And after some loops, when let's say the fit is almost stable, so you don't have much change after some iterations, then you, let's say, you understand what is the concentration of the elements. But this is valid only because typically this software works assuming some hypothesis. that the sample is flat, so you don't have any morphology, which becomes very important, the morphology, when you deal with low energy lines like oxygen or carbon, for example. These are very sensitive to morphology. These no, but these yes. Then he assumed that the sample is homogeneous in Z, so that you don't have layers, for example. And of course that the sample is stable. If this is not true, so for example, if in the sample that I showed you before, with a thin film of 40 nanometer of silver and titanium and oxygen over alumina or over silicon, this is not an homogeneous sample. So there are some tricks to account, at least in the case of the homogeneous film, let's say, because you can say to the software, okay, don't consider, for example, silicon, okay, is there, but don't consider it in the quantification. Or the coating, you make a coating, the coating of carbon, I know, consider it, but don't put it in the quantification. You can do something like this. But otherwise, at a given level, you cannot refine this too much unless you use much more complex software, which are made to where you can insert what is the structure of your sample, if you have layers, if you have clusters, spherical clusters, nanowires, and so on. And then by running calculations, you can simulate what is the spectrum and compare with your spectrum. But these software are more complicated, and of course they exist. Okay, if you learn how to use it, you can use it. But okay, it's not the typical software that you find together with SCM. Let's say like this. Anyway, these are the main things which affect the intensity of the peak. Let's see if there are questions. When materials exposed to high temperature welding, the metallurgy of the material changes. Is there any technique to study the live surface morphology characterization changes? Live. Okay, it depends on the temperature. If the temperature is moderate, so let's say 500 up to 800. Okay, there are also heating stage for SEM, which can go up to 1500. These are very exceptional systems, okay? You can find them, but it's not common, really. The highest temperature, which I know a heating stage can come, is 1500. Then maybe there are also other, which I don't know. This is what I know. Is there any technique to study less? Well, if you can manage to do it, to heat up, I don't know what is the temperature that you would like to perform your experiment. If it is within these ranges, then you can do it. Of course, my suggestion before starting using the heating stage is first try to do the experiment ex situ, no? To see what are the relevant, I see here 1400 degrees. This is, okay, yes, they exist. Probably you cannot go so high in a standard SEM because the risk of damaging is pretty high. But so you need a large chamber SEM. There is one in Germany that I saw, but probably there are also others. And you need shields for the secondary electron detector, because otherwise you can damage it. Okay, and if you are going to use also the backscattered, you need also probably some shielding for the backscattered, and then yes, you can do it. You have to find a heating stage which goes so high, and then yes, in principle, yes. Nothing.
Thank you, Professor. for answering all the questions in such a elaborative manner. We don't have any questions. With this, may I request Professor Mahesh Kumar sir to have his closing remarks for the today's session.
Yeah, thank you, Professor Matia, for explaining all the doubts, this one, which participants had. And with this one, we will close today's tutorial session. So thank you very much for explaining this electron microscopy techniques.
My pleasure.
Yeah,
Okay.
thank you. Yeah.
Bye-bye. See you.
Bye. Bye.